Recording here. Okay, cool. So, before I show you what I've done, are there any questions about either of these questions? Like, if there were struggles, where were the struggles? Or were there just many nameless struggles? Maybe. Okay, well, I'll just walk you through what we did here. Okay, so, I mean, there's a lot of preamble here as a car, blah, blah, blah. We're going to, the whole punchline is plot the following graphs given the information below. It wants a graph of original speed versus reaction distance. It wants us to analyze the graph from A to determine the equation, graph the original speed versus total distance, and to describe the differences between these two graphs. To really be able to describe the differences, if you don't put them on the same graph, or at least give them the same scale, it's going to be really hard to do. Like, I saw someone at lunch came to me and showed me theirs, and the graphs looked great. But because the scales were so radically different, it's going to be harder for this person who shall remain nameless to like really compare their two graphs. So what I did was I graphed and I put a little pink star here and a little green star here, and I threw them on the same graph. Now, the reaction distance here goes from 8 to 22. The total distance here goes from 18 to 92. So I wanted a graph that took me from, I went from 0 on the low end up to 100 on the top end. And if you would have noticed, there's actually 50 lines that go top to bottom. So what I did was I made my scale go up by 2 for each line. I put my, remember, I'm going to be pretty picky here with you guys, so I put my distance, I labeled the thing in meters. I've got my original speed down here in meters per second. And so I went up by 2s to give me everything. My original speed, it's the same scale. It goes up to 29 meters per second, so I took it up to 30 meters per second. And so I just did one tick is 1 along here at the bottom. So I went from 0 to 30, and I went from 0 to 100. Up here I went up by 2s. On the side I went over by 1s. And James, can I get the bottom light switch from you, please? Because I want to zoom this thing out, and it's going to be hard to see. Oh, is that better or worse? I feel like the eye doctor. Is that better or worse? Maybe James turn the light back on? Maybe James just stand at the light for a while? The flash will wash it right out. Okay, well, okay, thanks, James. You can have a seat. I'll leave it like that. I'll zoom in on the particular steps here in a second, but this is what my graph looks like. I've got this shallower pink one is my reaction distance data, and this much, much steeper green line is, what's the word I'm looking for? Much, much steeper green line is my total distance line. We were asked to analyze it to determine the equation. Well, to determine the equation, I need some, I need to find my slope first. So my slope calculation for the pink one here looks like this. This is what my line of best fit ended up looking like. I know the person who came in at lunch today was struggling with the line of best fit for the green one. They had nailed this one pretty good. So this is what my line of best fit looks like. You want something that looks similar. Yeah, I don't know what else to say about that. The points that when you pick points for a slope for a line of best fit, you want to make sure they are not data points. So I picked where it crossed the grid nicely down here at 5, 4 and up here at 33, 24. I did my rise over my run. My rise, we have to, including units here, really helps us see what's going on, because I had a rise is along these units here, and this is a change in meters. My run is a change in meters per second. So I have meters divided by meters per second. If you actually go out and do that and multiply things like we're supposed to, so like I got meters divided by a fraction. So meters divided by meters per second, I'm going to multiply by the reciprocal of meters per second, which is seconds per meter. And when I have meters times seconds per meter, my meters are going to cancel, leaving me with just seconds. So the slope actually represents a length of time. So what does it actually tell us? I found my slope to be 0.71. Hands up if you were close to that value. Angelina, what'd you get? Perfect. Anybody else? What other values do we get? Did nobody else do their homework? James, what'd you get? 0.77. What are the values we get here? Yeah. 0.72. Oh, you and I are really close. So with experimental data like this, even though you and I might have the same set of experimental data, because we're doing a line of best fit, and what looks good to you looks different to me, or what looks good to you looks, when what looks good to me might be different, and the scales we chose might impact things. The analysis of our data is allowed to change. As long as we're close-ish, that's fine by me. 0.7 seconds versus 0.8 seconds, like that might sound like a big difference, but it's a tenth of a second in the grand scheme of reality. Like, I'm willing to bet if we actually timed you guys that your reaction time is actually going to be worse than my reaction, than that tenth of a second. I'm willing to bet. So there it is, 0.71 seconds. So that's, if I analyze this, what does that mean? Well, that's the time it took them before they started hitting the brake. Then I did the same thing. I graphed it. My line of best fit is a little bit weirder for this one because I've got such a discrepancy in my points. Like I've got this one that's way above the line here. I've got this one above the line here. But then I've got this one and this one and this one are all below. So for this line of best fit, I got a slope of 4.15. Angelina, what did you get for the slope for this line of best fit? Did you get that calculation? Sweet. You're accurate. You can get that one. Who else gave me Eric? Okay, so you guys are all very close to mine. As long as you're within, I would say, as long as you're within like half a second up or down, I'm probably even maybe I'd have to see your line of best fit, but maybe plus or minus 0.3. So if you got a line of best fit anywhere between 4.45 and 3.85, I'm probably happy with that. I'd have to look at your line, but I'm pretty sure that that's the kind of the range that we're looking at here. We're cool calculating slopes. Like that wasn't an overly difficult thing to do. What was the hardest part of these questions? Yeah, Angelina. Oh, the y-intercept, right? So the y-intercept. Sorry, I meant for, okay, I guess I'm not there yet. We'll get there. At this point, I'm just looking at slope calculation. So this one is 4.15 seconds. If that's total distance, then this thing is total stopping time. But obviously, when the person starts at a higher speed, that total distance increases, even though the stopping time might be constant. Now, as Angelina just pointed out, let's talk about the y-intercept. The y-intercept here, what the heck does that even mean? Well, the y-intercept for this line here is actually pretty nice. Should the point 0, 0 be a valid option here? Like, should that data point be considered on this pink graph? What that would mean was that there is no original speed, and if there's no original speed, then there's no reaction distance. Does that make sense? Okay, so 0, 0 would be a valid data point here. Okay, that's cool. So what we can do then is we just extend this line of best fit straight back to see where it intersects the y-axis. Like we take the the y-intercept to be literally exactly what the y-intercept is by like punching the line through the y-axis is what I'm trying to say. So I'm down here at 0, this is 2, so this middle tick here, this pink line I drew right there, that was my best guess for where 1 would be between 0 and 2. And I figured that where I was crossing it there was halfway between 0 and 1. So I said my y-intercept for this line was plus 0.5. I thought that was reasonable. Angelina, what did you get for your y-intercept? Like just barely negative? Okay. This ultimately what this means, like, is if we think back to, oh, actually we can't think back to it. What? Because you don't do it in Science 10 anymore. What you're gonna see here coming up in the next couple days is a relationship that I'm gonna give you. You probably have seen it in math, a relationship between distance, velocity, and time. Where distance is equal to your velocity times your time. We've seen this conceptually before in math? Not nearly enough of it. Yeah, because you were in my Math 9 class. I know you have. Do you do this in regular 10? D equals VT? Or sometimes it's S equals RT, or D equals RT. Distance equals a rate times a time. Different math teachers call it different things. If you had Myers, I know you saw it. If you had me, I know you saw it. I can't speak for anybody else. Usually it shows up in Math 10. So if distance equals V times T, I've got my distance, I've got my T, and I've got my V. What does this plus 0.5 meters represent? Because there is no place in D equals VT for there to be plus anything. James? Thank you so much, James. Yes, this represents our error. In this case, our error in what, James? Yeah, our reaction distance. So the question, so the error in, did we actually record properly, or not even properly? How accurate were we? No, I shouldn't even say that. How precise, there we go, that's the word I want. How precise are we able to be when recording the distance that it took for the person to react? Half a meter is 50 centimeters. For a car moving at 11 meters per second, 11 times 3.6, it's almost 50 kilometers per hour. If we're out by 50 centimeters in that measurement, is that reasonable? Oh, totally. Absolutely. If a car's traveling past you at 50 kilometers per hour and then slams on the brakes, for you to say, oh yeah, they drove for this far before they hit the brakes, that's, to say that you're within a half a meter is pretty good. So yeah, that's what this piece here, this represents. So that's where y-intercept came from. For this graph, y-intercept makes a lot of sense. It's really easy. There was a reason why I did not ask you for the equation for the second graph. I don't know if you looked at the questions closely. I did not ask you to give me the equation for the second graph. And that's because the y-intercept piece here doesn't make a lot of sense. 0, 0 is not a point I would include on the total distance because the total distance is made up of some weird pieces. It's made up of a reaction distance and it's made up of a braking distance. And there's weird combination of things that's a weird physical situation, two different physical situations that are coming together to give us our total stopping distance information. And so this wildly negative y-intercept doesn't actually have a lot of physical meaning, and so the equation for this doesn't have a lot of really good meaning either, because we're acknowledging the reaction distance piece. I don't know if any of what I'm saying is making sense. What I'm trying to say is the analysis for this one it's a lot harder to do than just looking at this line because of what goes into giving us this last piece, this last data set. But slope works. We can find the slope. And then the differences between the two graphs. One's a heck of a lot steeper than the other. Their y-intercepts are wildly different. One can include 0, 0. The other should not. Even though to have no speed means to have no total distance. That conceptually makes sense, but it's still not a valid data point. Is there anything else, any other questions with this thing? If you weren't able to finish it, do you feel a little bit better about being able to go back and take a look at this now? Okay. Where I struggled with this stuff as a student in the past was with the line of best fit, and that was the question that was brought to me at lunch. Like, how do I know what my line of best fit is actually going to end up looking like? How do I know if this is a good line of best fit? And a lot of that comes with feel and being willing to commit. If you have a fear of commitment in relationships, in putting pen down to paper, if you're one of these people who doesn't want to try anything before you tackle a math question because you don't know if the route you've chosen is the right route, and you're frozen until you can see it in your mind, this is going to be a struggle for you. The quicker we can break you of that, the better. And you're like, you know what, just friggin' try it. As long as the line is a best approximation for the data that you've got, or a reasonable approximation for the data, you're good. If you want to be real neurotic, I can show you, if you want, on your own time, in my own time, how to do all of this in Excel. Like Microsoft Excel, I think Google Sheets will do it. I've never done it in Sheets, but I know Excel will do it. They will actually give you lines of best fit for data sets. I can show you how to do it. I prefer doing it by hand, but that's an option there too. So that was graph 1. Cool. Comments, questions, concerns, anything? Once, twice, 3 times, sold, flip the page. Question 2 says the total distance a lab cart travels during specific lengths of time is given below. So this is a lot easier. We've got one data set, we've got a lab cart, we've got some time, we've got some distance. I want to plot the distance versus time graph. So here's the plotting of my data. 0, 0 in this case would make a lot of sense at time 0. This thing hasn't moved yet. So I included 0, 0 as a data point, which also happened to be my y-intercept based on my line of best fit. I drew my line of best fit. I took my what's it called? My points that nicely intersected my graph. I made my rise-run triangle, and then I went through it. It says plot time, done. I've also got my distance in meters up the side there. I've got my time in seconds along the bottom. Determine the slope of the graph. I got 0.29. Did anyone get something different? What'd you get? Angelina, did you do this one? Okay. Anyone else other than Gary Carrot do this one? Tristan, did you get this one? Okay. Eric. 0.2857. That's really precise. I like it. Very, very disturbingly precise. And I'm pretty sure I rounded mine too as well to 2 decimal places, so 0.29. The units for this, if my rise is in meters and my run is in seconds, meters divided by seconds gives me meters per second, which is a little bit of a hint as to where we're going. This tells you that the slope of a distance time graph represents what? These are units of, which is a measurement of what concept? Speed. So the slope of a distance time graph is going to give you the speed, which is basically the introduction to the next unit that we're going to start hopefully on Thursday, fingers crossed. Today's Tuesday, right? Yeah, hopefully Thursday. What else did it ask me to do? Determine the equation. So because my y-intercept is 0, my equation is just distance. My y value is equal to 0.29 times time, my x value or x variable. And then I just use that to predict some the time to travel 2 meters and what would be the distance traveled in 18 seconds. So I just did my calculations right down there, just right on the graph. I made this thing huge. When I say use over half the graph paper, this is what I mean. There's my whole page, and I used 2/3 of it. Actually, I used almost exactly 3/4 of it. Make your graphs big. The tree is dead. Use the paper. Tiny graphs are really hard to analyze. The smaller you draw things, the harder they're going to be for you to analyze effectively. And that's just, going forward in time here. Questions about 2? Okay. Did we attempt our homework, or did we just give up? You know what? Maybe don't answer that question. You're going to want to actually do your homework for whatever reason. And if you have questions, feel free to email me. I also want to point out that I put the title up here. This fun little graph paper that I found actually has a space for your title. So I want title, I want axes labeled with the variables that you're measuring on them with the units, calculations done right on the page. I got my line of best fit, I got my data set. Like this is exactly what I want here. Comments, questions, concerns? Okay. Did anyone try 3? You did? How far did you get? Did you see it? You got to the point where it was curved and you're like, what the heck?
Yeah, I got to the point where I could draw the line of best fit.
Okay, so if you take a look at the data here, data gets weird. So this is the intensity of light in lumens emitted from a lamp recorded at various distances away. So 10 meters from the lamp, it was 100 lumens, 20 meters is 25 lumens, 30 meters is 11.1, 40 is 6.3, 50 is 4. We're not going to get into how light, the luminosity of light varies with distance. That's just not something we're going to touch in physics. That will, like, if you're going to look at that at all, it'll likely be something you address when you take like a full-on optics course, which I'm going to do a tiny unit on optics if we have time. I did a full semester-long course on optics as part of my university degree, so it gets you go wild. You might talk about it there. So the point of this data set is to show you guys what do we do with this thing? There is a tool that I am going to give to you. I want you guys to set this graph up. You got 3 sheets of graph paper. The 3rd sheet of graph paper, I want you to draw this. Get your data going on here. Label your axes, and while you're doing that, I'm going to hand out some tools here. Yeah. Yeah, absolutely. Hand them on. Oh yeah, they should be on top right there. Okay, cool. Yes. Oh, were you here yesterday? Don't take that one, that's my master. No, don't take that one, that's my master. If you're ever away, extras are always up here, guys. So some of you, you're going to need the problem set, and you're going to need the... paper. And problem set and graph paper. The photocopier, just 2 of you gentlemen who just took, mangled the graph paper, the lines are askew. If you want to repunch, it's on the mobile front of the back. Where is this? These, while you're doing that, these things have been living upstairs, and some of them have gone missing, so we're down to 5. Which isn't super useful. So we're going to have to share this next tool here. I've got 10 of them, so I should be okay. So while you're graphing this, I can do it with someone else. There's 3 of you gentlemen. That guy. Yes. You. So let's do that. Get the 3 of you. That corner. gentlemen. I'm gonna share this one.
Bro.
You pick your own. Do that one. And then you two. I'm gonna share this. And the three of us, Naya, Tristan, and myself, get this last guy here. Okay, so have we got our data points on our graph? Okay, if you do, lines of best fit are possible to draw not just with rulers, but there are other tools that have the same idea. So in physics, basically everything we do is governed by a particular set of fairly easy to predict mathematical formulas. When you take Physics 12, you're going to see that a whole bunch of different concepts are all related by a 1 over x squared kind of graph. And a 1 over x squared graph has roughly the same shape. I don't expect you to know what that shape is. You'll learn about it, I'm hoping, in Pre-Calc 12. But my point is, yes, there are a bunch of different concepts, but they have a similar shape. There are logarithmic shapes to functions. There are, you get the idea, right? I'm hoping. There's a bunch of very similar mathematical constructs that give us wildly different physical relationships. And what that allows us to do, it allows us to create tools like this. This is called a French curve because it's curvy and made by the French. Love them or hate them, the French scientific community and mathematics community has been one of the most powerful over the last 200 or 300 years. And they've given us this particular tool. How this particular tool works is we line it up similar to how you do a line of best fit. As you can see, it's not super precise. Like, we've obviously got some problems here. If I were to just draw the line as it sits right now on this curve, I've got 2 points that would be consistent, but one is way the heck out to lunch. And so what we end up doing, and this curve is built through a bunch of different mathematical functions replicated on this curve in different places. And so what that allows us to do, it allows us to move the curve around until we find something that actually does a fairly decent job of approximating our data. And so in this case, I've got something like this is probably the line I would draw. But then you can tell here at the bottom, things are starting to get a little bit weird. So I find a new location on this same French curve to continue the data. Oh, and you hope it doesn't slide on you. And so we end up with something that looks like this. And I can make this a little bit more pronounced. Now that I've got it, I can go freehand in a little bit just to make it more pronounced. Or better yet, actually do it in a different color. So I guess something looks like that. What a graph like this does is it's obviously not linear. Linear means it's a straight line. But having data like this, there's other useful pieces of information for this too. Like, we can start to estimate, well, if I was at different distances along the way, well, if I was at 25 meters, what would my light look like? What if I was at 15 meters? What would my light look like? As I get closer to 0 here, this is just going to keep going up and up and up and up and up and up and up. Conceptually, if I'm right on my source of light, what would my luminosity be based on this graph? If this thing's increasing as I approach 0, it's getting really steep. It's going to go up really high. Hands up if you completed Pre-Calc 12 or Pre-Calc 11. We do asymptotes in Pre-Calc 11, yeah? No? Is asymptotes Pre-Calc 12, James? Dang. Well, then I'll tell you. The implication here is that as this thing gets closer and closer to 0 in a distance, luminosity is going to get greater and greater and greater and greater, and greater much faster, to the point where at zero distance, we're right on our light source, we have infinite luminosity, is the idea here. Now, mathematically, we can do whatever we want. Physically, that doesn't necessarily make a lot of sense, but that's what the implication here is. And so we have tools like this. I'll pass this to you, Tristan, and you can use it here too, and then pass it to Naya. So share these things around with each other. Just so you can see, this is just showing you a different tool that exists for this kind of stuff. You likely will never use it again until you hit physics or like a university physics lab. You'll do stuff like this again, and you'll analyze graphs with your French curve of line of best fit. But yeah, no, I just wanted you to at least be exposed to and use once this tool that you'll see at some point in the future. Questions? Yeah. It's a curved line, so finding the slope wouldn't make a lot of sense. There are... Good luck, Connor. Good luck, Connor. Show off with your iPad. So Kieran asked a good question, like, what do we do with this? Are we able to actually find a slope? Well, slope doesn't have a lot of meaning here. But what we're able to do is we can start, this is where Connor might actually start to have a bit of an advantage, is if we were to actually plot this thing digitally or analyze this curve even graphically here, we would be able to start to work our way backwards towards whatever that mathematical relationship is. There's a bunch of different, because you guys, some of you are in Pre-Calc 11 right now, and lots of you haven't taken Pre-Calc 12. There's lots of different kinds of equations that could satisfy this. This could be an inverse logarithmic function. It could be a 1 over x kind of function, 1 over x squared maybe. There's a bunch of different equations it could be, and you will be given tools in the future as you go further in this stuff to be able to analyze these different curves and say, okay, we know this is what the physical phenomena tells us. What's the math? And you'll be able to go backwards and say, okay, well, this is the kind of equation. This must be the relationship that exists between these two different concepts, in this case, distance and luminosity. You don't have the tools to do that yet. It's a little more advanced than just finding slope. But conceptually similar, practically much more difficult. I don't know if that satisfies you at all. And that's where Physics 11 gets a little bit awkward, because there's lots we could do. There's a lot of power here. But you guys don't have the math to do it yet. You don't know what you don't know. So there, that's that one. And I didn't even want you guys to touch number 4, because 4 gets you graphing a bunch of different things, and it doesn't make sense to you why we would have a length of time, a length of our pendulum, and then why we would graph the square root of our length. That doesn't necessarily make a lot of sense. And I didn't want to bother trying to go into that and explain why we do that, so I just told you not to do number 4. There are valid mathematical reasons for it. I didn't want to take the time to go over it. If you haven't had a chance to use your French curve yet, smack one of your other 2 people who you're supposed to share the French curve with, because you have had plenty of time to, I think, all 3 of you to have graphed these things. Yeah, I just wanted you to use it once. So what I'm going to get you guys to do now, this is the end of our first little unit. This is math review plus sig figs and measurement and an introduction to, or a reintroduction to these ideas behind graphing. I'm going to give you guys a review assignment, your first chapter review assignment. You're going to do it. You're going to hand it in to me. I'm going to mark it. It's going to be great. Well, not so great because I have to mark it, and you're going to get marked on it. But this should be a gimme. There's some solving equations, order of operations stuff. There's some sig fig stuff. The only stuff that I didn't put on it from this first unit is trig. There is no trig on it, and there's only one graphing question on it. Yes, James?
There's a test tomorrow?
And I'm going to give you guys a test tomorrow on it.
Oh, like on everything we've already done?
On everything we've done.
Oh, that's easy.
It's not hard.
Why is it dual test day tomorrow?
Tomorrow.
Bro,
Fine, it's just a big quiz.
We have a pre-calc test. Bro, I have a pre-calc test tomorrow. Math is stressful. Bro, this is ridiculous.
Okay. Ladies and gentlemen, breathe. I normally don't care about the fact that you have multiple tests on the same day, but because I'm giving you less than 24 hours notice, fine. I'll move it to Thursday. But I've not given you an entire block tomorrow to work. Tomorrow, we are going to start, well actually this will work out really well. We're going to start kinematics, but we're actually going to start kinematics with a lab, which is going to give you more graphing practice. So that's going to be great. Actually, you know what? Moving this to Thursdays, thanks guys, that's a really good idea actually. We'll test on Thursday. It's going to make a lot more sense. And Cohen, I know you said you're going to be away tomorrow. So the lab you're going to miss is pretty easy lab. I'll have the materials down here and you can do it. If you want to come in during SLO, you can do it then, or, yeah, it's up to you. We'll figure out a time you can do it. Okay. Yes, ma'am. No. The trig I wanted to review because of where we're going in kinematics. All the other stuff is, everything from this thing is what the test is on. And there's nothing on the test that's not. Yes, sir.
How long is the test?
It's shorter than the review. It's like 2 pieces of paper, double-sided. Not really. This first unit, we finished basically in 4 days. Sorry? I do have a PDF. Yes, I can send it to you. Different sets. You can use any piece of. So Manuel asked a good question. He's like, well, what about all of these other different curves? All of these other different curves exist to mimic different mathematical equations, like general equations. Like you've seen at this point, you've seen the general equation for a linear graph: y equals mx plus b. This is our approximation for y equals mx plus b. Straight line. I'm hoping at this point you've also seen. You graph parabolas in.
Yes.
In 10.
You're gonna.
In 10? 11, okay? So if you don't figure out, you do a lot of parabola stuff in 11. There's one, I think it's actually this piece of this is parabolic. But then there's logarithmic, there's inverse parabolic on here. Like there's a whole bunch of, every different curved surface on this tool mimics a different mathematical relationship. Yeah. If you have a French curve, please return them up here. And I've got, that's pretty good. That's pretty good. That's actually pretty good. And I've given you, there should be reviews making their way down. If you don't have one, let me know. I've got extras up here. The rest of this block is for you guys to do this work. Tomorrow we're going to do a lab. Tomorrow is DCDA. So I have you guys ready for
Wait, DCDA?
Sorry? Thursday. So guys, this is good. One thing I didn't. Ladies and gentlemen, one thing I didn't do, guys. One thing I didn't do, is. One thing I didn't do is I didn't get you to put your name. I didn't put a spot for your name on this thing. So please put your name in the top right-hand corner or the top left-hand corner, one of those 2 corners of the thing I just handed out. There's not a lot of space for that first page. Hang on, this one until I get this down. There's not a lot of space on that first page, so I'm going to ask you to do your work for the first page on a separate sheet of lined paper, gentlemen in the back. Did you hear what I just that, gentleman back there? First page of the review, I want you to do a separate sheet of paper. You're going to staple it to the back. Everything else there should be space for in the handout that I've given you. It is due the day of the test, so Thursday. Because I'm going to test you on this stuff. And that test should not, the test is not even going to take a whole while. Like, it's not very bad. That's your first one. Yeah, what? Oh, the third question. Well, your spot needs to go from 1 to 5, so you can go 1, 2, 3, 4, 5. Yes. And this one you need to go from 0 to 1.5 basically. So you could go, if this is all you're using, go up, 0, you can do something like 0.5, 1, 1.5. Okay, come on, let's get to the PDF of this. This is a work block. Feel free to work with the people sitting around you. You can talk to me if you want help. On your mark, set Gaber. Tomorrow we do lab.
I left my water bottle downstairs.
Go
Can I
get it.
grab that and go to the restroom?
You betcha. Yes. Yes.
For the best fit line, so I'm like so confused. Do we always like start from 0 and
No. You
because
never start from anywhere.
yeah.
You use the data that you're given to
Like for this one,
Like
like
for
when
this-
I looked at yours, like
Yeah.
it was, I didn't. Then I can't find like the y value of it.
what do you mean?
Like for this one.
The
like
y-intercept?
The
Oh, the green one?
Yeah.
You're right. I can't either. And I didn't ask. I very intentionally did not ask you to find the equation for this line.
Yeah.
That was intentional.
So every time we make a best fit line, we don't start at
No,
like 0.
only if the point 0, 0 makes sense to use as a data point.
Okay.
This one it does, and it just so happens that, like, I was like my line of best. I could have probably drawn my line of best fit straight through 0, 0. But I, for whatever reason, when I was drawing it, chose not to. But I didn't ask for the equation for this one because I knew this is what this one was going to do. It's going to go big and negative, and that line of best fit actually isn't going to make any sense. Or sorry, the y-intercept isn't actually going to make any sense. The line of best fit always depends on the data that you're given within the range that you're given it. So this is the data we had, so this is the data that needs to mimic, that the line of best fit needs to mimic, regardless of what happens other places.
Okay.
Does that help at all? Okay.
I'll try the other question.
Okay. The very last question in the review I just handed out is another one of these graphing questions. So if you're struggling with that stuff,
Yeah, the best fit line's only like
yeah,
is confusing.
yeah. Because you've never been told, oh, just kind of fudge it in there, because your data up to this point has always been perfect.
Yeah.
And this now you're not.
You have to feel like the first equation for because I'm new. Or I can just put.
No, you're fine.
Okay.
Yeah, you're fine.
For question number 2, the graphing, why did for question F, why don't we do the y-intercept? Why don't we add the y-intercept to find question?
My y-intercept was 0. You would. Depending on whatever your equation is, you would.
Okay, because mine was 0.02.
The only reason, because my y-intercept was 0, it wasn't included in my equation. So when I substitute values in there, I didn't have to do anything with it.
This is for.
This is,
Oh,
you
yeah.
said question 2, right?
Yeah.
Yeah.
Okay.
So if you had distance equals whatever your slope was times time plus, I don't know, point something,
Yeah, I had point.
0, 1, 0, 3,
Yeah.
then you'd have to include that in these two equations, and it would.
But then I didn't get a similar answer to you. I got 5.07.
What's your slope?
My slope was 0.28.
Oh, really? Let's see.
I mean, it could just be like a math error, but
0.28. .97. Oh, 2.8 is 7. So you got 7 here and 6.9. That's good. That's really good.
and how I found it was I just moved everything over. Like I isolated S
Yeah, that's what you're supposed to do. Yeah,
Okay.
that's good. And then for this one, so you had 18 times your slope plus 0.03. How come? Where did that 35 come from?
Oh, that was from my previews. That was my other Okay, no, I know what I did wrong.
Okay.
I had,
'Cause
that
that-
was my first, when I tried it yesterday, but then when I tried it again, I got the right answer, and I guess I didn't change it for that.
Okay, so I'm wondering, like, I mean, even this number isn't bad because, like, 5.07 to 5.22,
See, I think I did. I'll go get my calculator.
7 to 22 is, what is that? 15 centimeters. I mean, it's not great, but it's not terrible. But yeah, what is 0.28 times 18 plus?
See, that is, I did the calculation right. Like, I added the point.
Yeah, no, I think you're fine. Like that's 15 centimeters over a distance of 5 meters. So my calculation says, well, the car is going to go 522 centimeters, and your calculation says my car is going to go 507 centimeters. Over 500 centimeters. If we're different by 13 or 15, whatever.
Okay.
That's nothing.
Okay.
Over 5 meters. That is such a small distance. Over 5 meters, you're great. Don't worry about it.
Okay. All right.
That
Thank
is
you.
your, yeah, that's your,
Yeah.
both of that's your paper.
Okay, thank you.
You're good. Okay.
Not again. Shut up.
Okay. Yes. Oh, Connor, I keep forgetting. I need something of value. I will trade you. Sure. There you go. Connor. I keep forgetting.
While you're getting that hooked up, can I go outside really quickly? Send a message to my grandma.
You betcha.
Thank you.
Your grandma, how dare you? You could. Make you a terrible grandson, but you could. .28, .29, like question number 2, or the second graph on number 1? Yeah, I think I got .28. Ish.